This is going to be part 5, and we're doing this on the same day that we did part 4, where we were kind of wrapping up the electrical design, the first look at it. In later sessions, we'll probably go back and discuss electrical design in a little more depth on certain aspects, simply because when we start looking at the program for the compact logics or for the panel view, it will probably be relevant to discuss some of the electrical design decisions that we made earlier and why we decided the way we did. Right now, what we're going to look at is the panel design. Keep this firmly in your mind. If you're looking for perfect circumstances where everything goes in order and just ticks off one thing after another, you may find that once or twice in your career, but usually there's issues. In this case, this project was started by someone else. In this current marketplace, there aren't enough people to do electrical design, there aren't enough people to do panel build, there aren't enough people to do electrically assemble the machine, and there's definitely not enough people to do the PLC programming or the HMI programming or the commissioning. There aren't enough people. So if you're new to this, you're looking at a bright future if you stick your nose to it and stay at it. But if you think you're going to watch this series of videos and go get a job as an electrical designer and you've never done it before, it's unlikely. The best place to start is doing the CAD work. So if you learn the SkyCAD package or a CAD package to do electrical design, the designer is going to give you sketches or going to give you an existing drawing set that they marked up. So in other words, they give you the electronic version, you open up on your computer screen, and then they give you a printed drawing set that's been inked up with red markings and notes how they want you to edit the existing drawing set to match the new project. In this case, this one, the panel was already ordered. This project has 3 robots on it, and they had already cut the bottom end of the back plate, the panel, off to make room to put the 3 robot controllers inside the enclosure towards the bottom, which meant that the enclosure had to be quite deep. So there were a lot of challenges. Bottom line, the panel was too narrow, period. But we still had to make it fit. Would have been better to have gotten a whole new panel and start over on some things? Probably. But in this particular situation with industrial control design, build, install, you're going to have to make some tough choices. We made some tough choices. So let's look at the panel layout, and I will point out some of the sacrifices that we had to make. Now keep in mind, I have not had to do electrical design or panel build or electrical assembly for probably 15 years. I stopped doing it 15 years ago or more because the market was so good for doing PLC programming and HMI programming, VFDs, barcode readers, vision systems. I was a certified vision integrator at one point. So I got off doing all the high-tech stuff, and I got away from doing this end of it. I made the best choices I could. Let's look at them. This is the panel layout almost as it sits now. We've already made some changes, moved some stuff around, but you can see width-wise that it is too narrow. And one of the things that caused it to be too narrow, if you look down here in the lower right corner, you see all these 2-pole fuse blocks. So we have one set of fuse blocks for each of the 3 robots, and then we have a set of fuses for the epoxy dispense system. So there's another completely finished sub machine that dispenses epoxy, 2-part epoxy, and it has a micro 830 PLC in it. So it's its own complete separate machine, but we run the power through this fuse block down here. So from this main disconnect, we can control power going to that epoxy dispenser. Well, these are 600 volt, but this is a 240 volt system. And we ordered 300 volt fuse blocks, and they couldn't get them. So we accepted 600 volts. Since then, we found another source, or maybe they came back into the supply chain. So we're going to redo this corner down here with smaller fuse blocks, which means we can move this wire duct over a little bit and create a little more space here between our safety circuit and our PLC on the end. So start in the upper corner here. What you can't see is this is a surge trap up here that hangs off of the 3-phase coming in. So the power does not pass through this device. It is just hanging there as a filter that traps any sharp surges that come in from the outside. And then we pass through a 3-pole fuse disconnect. This is where the square rod goes in that goes through the door. We got 3-phase coming in, going through this filter, line filter, and coming out and going to our power distribution. And from the power distribution, cheated a little bit here, we're running up 1 phase up here to this transformer, this power transformer, and there are fuses mounted on that power transformer, 2 of them for the primary, and then here's our secondary fuse, and it is basically would go to this power supply, this 24 volt DC power supply. As it turns out, this power supply has 240 volts input, so it's now connected directly up to the power distribution. And here we have the 24 volt DC distribution. So the DC is, the terminals for the DC are up on the top of this power supply that you can't see, and they come down here. And you notice that there are some red, you see the little red spots in here? We can zoom in on this a little bit. So we have red and we have blue. So I'm using blue for common and red for plus, just for the terminal blocks. Now these are the 1492P terminal blocks. They're spring clamp, but what's cool about them, this particular block here is the common coming from the power supply, and this one over here, the thicker one, is the plus 24. And then there are jumpers between this thicker block and these breakouts, if you want to call them that. So there are 3 terminal blocks here, each with 6 spring clamp insertion points that are jumpered to this main 0 volt DC connection from the power supply, which means we can drop 18 0 volt connections right into this small space. And over here we have the same thing but for plus 24. Then of course we have some ground connectors and end anchors. This is open right now because we are missing some of our 1492P fused terminal blocks, and they are spring clamp, and there's a little fuse holder right here on top that you can swing out like a switch, then open up the side, and they hold 5 by 20 millimeter fuses. We're missing some. They were on back order. One of the major challenges for this whole project from the beginning was the lack of availability of traditional components that we would order for the design. So it was designed with the traditional components. Then when it come time to order them, a lot of it went on back order, so we had to make some choices, as in color of terminal blocks, jumpers, jumper colors, control transformer, fuse disconnect, the distribution block, fuse blocks, etc. So there are a lot of compromises here. Now this is the only space left on this panel, and even that wasn't going to be left, and it's getting used right now. And we were going to use this space over here on this DIN rail and this space for the barcode readers and power over Ethernet injectors. That was all going to be in this spot right here. So this panel was jam-packed. It's just way too tight. Down here in our safety circuit, these are all force-guided relay contacts. So each one of these is a K1, K2 pair. So K1, K2, K1B, K2B, K1C, K2C, K1D, and K2D. So these are in pairs of K1 and K2, and they are strictly normally closed contacts that we're using for a lot of safety interface. We've got an Ethernet module mounted onto our 440C CR30 programmable safety relay or controller, whatever you want to call it. It's not really a controller, but it is really a micro 800 controller in red plastic. But we're using an Ethernet interface, and we're using a plug-in module that has 4 in and 4 out. So we could expand the number of I/O to these terminals that you see on the top and down here on the bottom. We didn't have room for all of the K1 and K2 expansion here, so we had to put some up here. So these two relays up here, this is another K1 and K2, all integrated with this. Now anything that you see red wires, red terminals, red plastic, that's all safety. Even these coming from fuses up here, this red wire is coming down into the safety circuit. This red wire is supplying power probably to this CR30. So any red wires you see up here or anywhere are all safety related. The safety circuit is always the most troublesome to troubleshoot. I shouldn't say troublesome, but people seem to understand it the least and therefore have the most trouble in troubleshooting it. And this is a fairly complex safety circuit. This is the disconnect, a little closer look. There's the surge trap up here. You see there's 3 poles, and we don't have this wired up yet, but we will. But you see this hangs off of the 3-phase. The 3-phase doesn't pass through it. You see there's no terminals over here on the right side, only the left side. So it's a filter that hangs off this 3-phase. And then coming out here you go to the line filter, line reactor, whatever you want to call it, and then from here to the distribution block. Variable frequency drive distribution block. As I told you, these fuse blocks here are all too large, and this one was the only thing that we could find that was small enough, 300 volt rating, that would fit in there, but then we couldn't find the right fuses for it. We've since taken this out and we've gone to a different style fuse block with a different style of fuse. The PowerFlex 525 variable frequency drive needs 3-phase power coming into it. It needs the safe torque off connections, that's the 3 red wires coming from over here in our safety circuit, and then it's going to have 3 terminals underneath this cover that go out to the motor. But it does have sufficient venting space on the bottom and on the top. A little closer look at our DC bus, if you want to call it that. Remember I told you that this heavy blue wire here comes from the power supply 24 volt DC output into this large block on the end, and then this large block is jumpered. You can't really see them up here, but there's jumpers up here that jumper to these 3 blocks, each with 6 individual insertion points for spring clamp. So all of these blue wires here are carrying plus 24 volts down into the panel. This is a little bit easier to see. So this section right here is identical to this one, but this is where we have the common coming from the power supply in here, and then this is jumpered. You can see the blue jumper right there, and then all 18 of these are points of contact for 0 volts DC throughout the panel. And again, these are our small glass fuse. These are blown fuse indicators, and you grab this little tab up here and you pull it, out and down, and it swings this out like a knife switch, and then you can pot down the side and put in the glass fuse, 5 by 20 millimeters. And we were missing some more fuse blocks that we need. And again, these are a K1 and K2 extension from our safety circuit. And this is our safety circuit. You can see terminals 0 through 11, and then down here 12 through 21. And then here's our expansion I/O. We haven't used them all. On this panel, 273 is plus 24 and 275 0 volts DC. You would notice that if we went back and looked at the drawing set, you'll see that's wire 273 and that's 275. So that's one of those fuses up at the top there that has the 1492 fuse blocks that swings down and has a glass fuse on it. Remember, these are pairs of K1 and K2. So every other one, K1, 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 K2, 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 K2. This pair is A, B, C, and D. Our L27 ERM, QBFC1B. The ERM means Ethernet redundant and motion. So this controller has a motion planner. It supports motion by way of Ethernet. We currently don't have any servos on this system, but price-wise, there really wasn't much difference in price between buying a Compact Logix that was an ER, Ethernet redundant, or this fixed I/O unit, ERM, L27 ERM. So we are using quite a few of the embedded I/O. You see blue up at the top there, that's input, and you've got 16 inputs. That would be IQ16. Right below it is an OB16. Then you've got high-speed counter. What you don't see, and there's no LEDs for it, and that is down below here towards the bottom of this terminal strip. On the right side is analog in and analog out. So there's 4 analog in and 2 analog out, voltage or current. This is all spring clamp insertion. These terminals, you can see the tab there. You can pull these terminals out for ease of wiring or for swapping out the controller. And we're not going to elaborate much on this controller other than we added the common as a bus right here. So we come down from up above and we have a 0 volt DC plugged into this first piece. It's a little wider. See, that's a little thicker. And then we have a dozen insertion points, spring clamp, for 0 volts. You always are going to need a lot of 0 volt connections on these control panels. And of course we have a Ethernet switch here. This is an unmanaged switch, and we don't have everything plugged into it right now. Obviously we have the processor. The purple goes up to the safety circuit. The blue goes to my laptop. I'm sorry, the green. So the blue goes to here, the purple goes up to the safety, and then the green goes to my laptop. Okay, this is a quick look at some of the terminal strips. Now notice that there is only a ½ inch of space between here and the wall of the enclosure, the actual side of the enclosure. You're not getting your fingers down in there to do anything. There's not even space to tuck the cabling down in there. And if we weren't using these spring clamp type terminals, the narrowness of this panel would have been exacerbated. It would be really bad. So what we tend to do is we use jumpers if we need multiple connections from the same device. So we typically use blue for inputs, green for outputs, and then red for safety. We did not have access to any black terminals or any gray terminals. I would ordinarily have used a few more colors, but the red is all safety. However, some of the blue is input and some of it is just DC. These are really nice terminal blocks. Here is the terminal block arrangement for the guard doors. So this, the fence, if you like, going around this assembly fixture that has 3 robots in it, has 3 SensaGuard switches. And these SensaGuard switches are connected, and we did go over that in an earlier discussion. They're connected in series. And if you go back, well, we can go look at the drawing. So you see here we've got 24 volts DC coming in. It's going to these 3 connections. And notice that that 24 volts DC goes to the brown on both of these, but the other voltages, yellow and red, that come in here come out of gray and pink and then come in yellow and red on each succeeding SensaGuard. So all these connectors right here, except for the fuse, are all represented right here in these 3 sections. And we used end anchors to kind of separate them. That's kind of a waste of DIN rail space, but I wanted to keep this easy to troubleshoot. So this is the top SensaGuard switch. That's why it has a few more terminals, and you can see 3 of them jumper together right here. And if you went back to the drawing, you can see that these 3 are jumper together right here. And then you don't have any more jumper together. So these 3 are jumper together, and that's why there's more terminal blocks here than here. Now, another thing to point out is that coming from each of these SensaGuard switches, we have a non-safety aux out going to the PLC. So that's this white wire right here that's going to 302.1, 311, 321. So these are not safety outputs to these inputs on the PAC. So here you see 3 blue terminals. That's because those are inputs to the PLC, but they're not safety inputs. That's why they're not red. Down here we have the expansion breakout board for 1 robot. So this little Wago breakout board here with 68 terminals on it. Then you see this connector here. This goes to 1 robot controller. This is a breakout board. We have the e-stop circuits interfaced into this board that goes to the robot. Each robot has the capability of doing an e-stop, but only when the pendant is plugged into that robot. And there's only 1 pendant. When you pull out the JRM connector on the robot and plug in a cable to this connector on the PLC panel, you basically are using the PLC to jumper those e-stops. So 2 of these terminals represent the e-stop condition of the robot back to the PLC, and the other 2 terminals represent the main control panel e-stop out to the robot. So if we went back to the safety circuit, some of these K1 and K2 combinations are going down there to the 3 robots to tell the robots that somebody hit an e-stop coming into this device. This represents the entirety of the interface to the robot other than power. And you see there's not really that many connections because most of it's going to be done over Ethernet. These 4 red terminals are robot number 2. So you can see this is robot 1 right here, and this is robot 2. I'm sorry about the blurry photo, but I'm in my studio. I'm not at the customer site, so I can't go take a better photograph. Okay, that's about all I can say right now about the panel build. And so the next discussion will be the electrical build and changes we made to the panel during the panel build.